Hi, my name is Jesse Natalie, and I'm here today to talk to you about the work that we've been doing using Mesa to build mapping layers. So this talk is going to focus on the 5 W's, the who, what, when, where, why, and how. So first off, who, basically all the people that have been involved in this project. I wanted to give a major thanks to all of the people who have helped. So from the Microsoft side, this has been mainly me and my coworker Bill. Our PM Angela has been helping out. And then we've been heavily helped by Collabora. So some specific names: Eric, Daniel, Gert, Louis Francis, Boris, and Ellie have been invaluable in trying to get this project up and running. So what am I actually talking about when I say mapping layers? What we have built is basically 2 API mapping layers, OpenGL on top of D3D12 and OpenCL on top of D3D12. So OpenGL on 12, as we call it, is basically a Gallium driver in Mesa. It looks very similar to Zink, if you've heard of that. OpenCL on 12 is somewhat different. It doesn't necessarily leverage the OpenCL API implementation in Mesa, but it heavily leverages the compiler stack out of Mesa and expands on a bunch of work that's already been done there for the Clover OpenCL implementation. The runtime we are building separate from the Mesa codebase. We're basing it on top of our D3D12 translation layer, which is the core of our other D3D12 mapping layers. Specifically, we have a D3D11 on 12 and a D3D9 on 12 mapping layer that use it. So when? This project has been underway for roughly a year. Some of you may remember at last year's XDC there were some mentions of some Microsoft folks, and it wasn't really elaborated. We probably didn't talk to anybody, but this was the primary reason that we were at XDC last year, was kind of getting to know what the space is like, learning who's who in the Mesa community, and this was also our first face-to-face meeting with Collabora. So moving on to the where for this project. I'm not really going to talk about where in the world we were working on this. I think it's relatively obvious that the Microsoft folks have been in the Pacific Northwest of the USA. Collabora folks are hosted all around the world. Instead, I'm going to talk about where the source code has been, because that's kind of funny, actually. So at first, we started this project in secret. We had a private GitLab instance that was hosted by Collabora for us. Within the last maybe 7 months, we shifted to full open source. Eric from Collabora hosted a freedesktop.org GitLab fork of Mesa for us. And all of our development has been happening there ever since. And over the last several months, we've been working on upstreaming as many pieces as we can to the core mainline Mesa repository. And hopefully by the time that this talk is actually being given, we will have our D3D12 driver in mainline Mesa. So why? Why are we building mapping layers? Why are we building them in Mesa? There's a lot of whys to answer here. So I'm going to first talk about the Windows reasons that we're building this. The primary reason that we're building mapping layers for OpenGL and OpenCL is to support devices which don't have any Windows drivers for these APIs. We want OpenGL and OpenCL to work across our entire ecosystem, and unfortunately there exist devices that just don't have support today. So for example, Qualcomm doesn't currently provide OpenGL or OpenCL drivers. If you're running a device that has no GPU driver at all, you do get D3D support through our Warp Windows Advanced Rasterization Platform software driver. So if you're running in a virtual machine, for example, you have Warp, but it doesn't have an OpenGL or OpenCL implementation. If we have new devices that are coming online, it's a significant burden to write yet another API or driver implementation. So we're hoping that this can help accelerate the bring up of new devices. A secondary reason that we're building this is to enable our partners to eventually transition to using mapping layers instead of native drivers. This is obviously not a requirement, but from our perspective, it can potentially make things easier. It can reduce the development burden, the cost of supporting Windows, if you have one less driver to maintain. Another reason is interop. Being able to use a D3D device and be able to also issue GL or CL operations against it as well. That can potentially be relatively expensive. You have to create multiple devices, you have to use shared resources, you have to do shared synchronization objects. It's a lot to manage to make it work. We're hoping that by having mapping layers, we can provide an easier and simpler story for interop. And access to debugging tools. D3D12 has world-class debugging through PIX. There's also RenderDoc. Some tools out there do have support for OpenGL. Support for OpenCL is not great. But by being able to run an existing application through these mapping layers instead of a native driver, you can automatically get debugging support through other tools. So continuing on, we also want to support this for WSL, which we've talked a bunch about already today. One of the primary reasons that we want to support this for WSL is it means that we only need to provide one user mode driver from a given vendor in order to get a wide breadth of API implementations. And then why did we pick Mesa? When we were first starting this project, we were brainstorming how do we implement OpenGL, how do we implement OpenCL. When we were talking about OpenGL, it really doesn't make sense at this point to try and bring up a new OpenGL implementation from scratch. There are so many years of compatibility quirks and extensions and all kinds of things, and really, if we weren't using Mesa, this project just wouldn't have happened. This was the only viable approach to get an OpenGL driver. We weren't sure how we wanted to do OpenCL, so we talked to Collabora, and they suggested that we should use Mesa's compiler stack for OpenCL, and I'm definitely happy to say it was absolutely the right call to go that approach. It's been invaluable. So moving on to the how, which is the interesting part of the talk. What did we actually build? So what we've built consists of 4 primary components. First is a near to DXIL translator, where near is Mesa's intermediate language for shaders, and DXIL is D3D's intermediate language. DXIL stands for DirectX Intermediate Language. Very creative. DXIL is LLVM based. It's based on LLVM 3.7. So we built a custom LLVM bitcode emitter rather than using the LLVM codebase to do it for us. We built a Mesa Gallium driver, which is our D312 OpenGL driver. It implements the Gallium pipe interface and translates it to D312 API calls. And it's basically exactly the same thing that Zink is doing for Vulkan. We built a D3D DXGI Windows WinSys, which enables us to use DXGI swap chains for present, which significantly improves efficiency and performance. And then we built a CLC to DXIL compiler, which goes through this crazy compilation pipeline from OpenCL source through the Clang compiler to Spear, through the SpearV LLVM translator into the SpearV intermediate, through Mesa's SpearV parser into Mesa's near intermediate, through the near to DXIL path, and finally we get out DXIL at the end. So the near to DXIL converter, a few comments and details about it. Why didn't we use LLVM directly? DXIL is based on LLVM 3.7. We already wanted to have an LLVM version built into these components, but we didn't really want to stick with LLVM 3.7, which meant that we really couldn't use LLVM for both at the same time. They would conflict. The LLVM bitcode is unfortunately a very difficult thing to deal with. It uses all kinds of variable-sized fields, and I'm not just talking about 8 versus 16-bit, I'm talking about 3-bit and 7-bit fields. Lots of unaligned data. It's kind of messy. And then on top of the regular constraints of the LLVM bitcode, we also have the DXIL validator, which makes sure that it is a particular layout. For example, metadata ordering needs to be in the right place. So what we built is basically a 2-pass approach. First, we translate the near into a bunch of data structures which match DXIL semantics, and then we do a pass over those data structures in order to emit the variable bitrate data. And then on top of that, the LLVM IR is actually wrapped up into another container, which has a bunch of additional chunks for things like runtime validation, so that D3D doesn't have to parse the IR directly. They can basically just pull out data and make sure quickly do validation against what's going on. The D312 Gallium driver, more or less self-contained. It deals with tracking state, allocating resources, managing command lists, all that kind of stuff. It has a lot of features that it needs to emulate, things that OpenGL requires that D3D doesn't necessarily implement. For example, wide points is something that has been deprecated since D3D10. The concept of an interleaved depth stencil buffer doesn't exist in D3D12. Instead, D3D treats depth stencil as planar, where depth and stencil are completely separate. We were missing some vertex formats that OpenGL requires. For example, this RGB 10.10.10.2 format. GL has ability to support 8-bit index buffers. D3D only supports 16 and 32-bit. GL has the ability to do two-sided polygon rendering where the fill modes are actually different for both sides. So you can do, for example, wireframe on one side and solid filled on the other. I'm not sure exactly why you'd need to do this, but it's supported. So we had to emulate that. The concept of provoking vertex. D3D's provoking vertex is always the first vertex of a triangle. GL's is by default the last, but is actually configurable as well. So some emulation was needed there. The concept of combined images and samplers. D3D has completely separate ideas of a texture and the sampler that you're going to use to read it, where GL kind of conflates the two and treats them more or less as combined. So there is some work needed to separate those out. Point sampling of integer textures is actually kind of interesting, and this is one that we didn't foresee up front. But D3D only has the ability to do loads of integer textures as opposed to sampling. And specifically what that means is that if we want to do access with normalized coordinates, or if we wanted to get border behaviors, for example, clamp or a border color or repeat, we actually needed to write additional shader code to make that happen. Talking about the Windows system. So on Windows, Present is very complicated. If you're interested in specifics, I actually have a YouTube video that kind of covers what's available on Windows 10. There's a lot of options. So as a driver for OpenGL, we have access to a couple of callbacks from OpenGL 32. But unfortunately, they're not very useful for a mapping layer. You kind of really need to be a proper driver to be able to access them, which means that our only other option for getting contents onto screen was to use GDI, which is Windows' very old, the first iteration of graphics on Windows, which basically requires copying contents from your GPU render target into a CPU accessible surface and wait for the GPU to be done with that. And then you can copy that into another GDI surface, and then you can copy that into the window. And it is obviously very slow. That's a lot of copies, and there's a lot of synchronization overhead to make that happen. So DXIL allows an efficient queued present. You don't need to wait for it. You don't need to do a bunch of copies. But unfortunately, Mesa likes to be in control of the buffers that it uses for rendering, or the buffers that it uses to back the frame buffer. Where DXIL needs to be the one that actually allocates its own resources. So we were able to come up with a somewhat messy interface so that DXIL can allocate things and hand them off to Mesa. But it works, but it's not great. OpenCL. So as I mentioned earlier, the only thing that exists in Mesa today is the OpenCL compiler. The runtime is separate. So the OpenCL compiler is a very complex compilation pipeline. Fortunately, we didn't have to invent it entirely. Clover, which is Mesa's OpenCL runtime, did pioneer it for us. At the time that we started this project, Clover's support for OpenCL was kind of sub 1.0. It wasn't complete, and it definitely wasn't up to OpenCL 1.2, which is what we wanted to support. So we had a bunch of work ahead of us to kind of improve things. Part of that, there's a bunch of crazy conversions that you can do between floating point and integer values. You can do round to nearest even, round down, round up, and round towards 0 on every conversion from every possible type to any other possible type. There's support for work item offsets was missing, so CL has the ability to basically say this work item is going to start at a particular offset, and that just wasn't there. OpenCL doesn't technically require images, but all of the real-world applications that would want to use OpenCL for image processing, for example, would need image support, and that was not hooked up in the compiler, so there was a bunch of work needed for that. OpenCL requires implementing a very robust library of math functions, all the various trigonometric, sine, cosine, arcsine, hyperbolic, arcsine, all that kind of stuff. And it has very strict precision requirements for all of that. Fortunately, there exists an implementation available that we could leverage. It's called libclc, and it's inside of LLVM. So we did a bunch of work to enable our Mesa compiler to embed those implementations for us. Near had some pointer support available out of the box, but it definitely needed some more work to be able to support all the kinds of crazy things that OpenCL can do. And then we also had a bunch of DXIL-specific shortcomings to work around. So, for example, DXIL does not have pointers at all, where OpenCL very much requires pointers. They're a core part of the way that you would write a kernel. So we were eventually able to figure out how to use the near lowering passes to be able to convert OpenCL pointers into a buffer index and offset, so that we can hand it to DXIL. And we have been contributing all of these things that we've been working on back towards upstream Mesa. And as a result, we've actually been helping to significantly accelerate Clover's progress for supporting all these features as well. So how will customers get their hands on this? Our current plan at this point is to ship as an app package in the Windows Store. So this is what the landing page for that's going to look like. In insider builds, as well as actually serviced into the stable release, we have updated the OpenGL and OpenCL ICD loaders. So when you try and actually initialize these APIs, they will actually check to see if this particular app is installed on your machine. And if they are, and if you don't have a native hardware driver available, we can actually go and pull these mapping layers out of this package and use them. And our current hope is in maybe a month or so's time that we can actually have a version of this live and available for end users to actually try out. And kind of proof of life, we're very happy that we have a bunch of apps actually working already. I don't have a live demo to show, but I do have at least a quick screenshot of Blender running OpenGL on 12. This is on a Qualcomm device, where not only was this app not GPU accelerated before, but this app didn't actually run at all. Attempting to run Blender on a Qualcomm device just failed because there was no GPU or no OpenGL support available. So yeah, it's alive. We've made a lot of progress. This has been a really fun project. I've been really happy working with the Mesa community, and I look forward to continuing to work with you guys as we move forward to adding new features, getting OpenGL 4.6, OpenCL 3.0, and getting WSL support as well. So thank you.
Okay, and now it's time for the questions.
Oh, there we go. Now you should be able to hear me.
Absolutely.
Okay. So I guess I can quickly go ahead and summarize discussions that happened while the video was playing. There was a quick question about using LLVM 3.7 for DXIL. Are there any plans to upgrade? Unfortunately, it's a little bit difficult to do that. D3D drivers are expecting to get LLVM bitcode that came from a 3.7 version of LLVM. So yeah, upgrading is something that is desirable. We could potentially do it in a new version of DXIL, like a shader model 6.7 or something. But unfortunately, the DXIL compiler is a fork of Clang as opposed to integrated into upstream Clang. So it's a pretty significant chunk of work to get a DXIL compiler on a new version of Clang. It's basically going to be reporting it and reforking it off of a new version. Let's see, was there anything else? It's just some comments and discussions about naming. That near stands for new IR, and DXIL is roughly as creative as that. And also, Jason mentioned that the DRM, DRI3 and DRI2 paths for Mesa's GL state tracker do have support for client allocated buffers. But yeah, at a high level, it's basically just the WGL Windows path that doesn't.
So if anyone has a question, it's about now is a very good time.
I guess while we're waiting for questions, I can go ahead and say that I forgot to call out a huge thanks to Jason Ekstrand and Carol Herbst, who have been instrumental in getting the OpenCL implementation up and running.
Okay, well, I guess that was, it was a very clear talk, so congratulations.
Thank you.
And I guess in 10 minutes we're going to be having Bas talking about profiling on AMD GPUs using tracing. Thanks a lot.
Cool. Thank you.